for the title of the talk, and that was quite a long ago. I thought that I will tell you about some very new experiments in Vortex state, and I wanted to connect that to the questions of the zero bias state in the vortex core that has been seen and argued in iron-based superconductors, so-called Majorana states. So this experiment was meant to be in optics, so it's an optics perspective of that. I'm going to tell you some results that we have. I'll tell you the motivation. I don't have very solid conclusions on this topic, but what I decided, I will split this talk in two halves, and the second half is really going to be about the quadruple excitations in superconductors, because I believe that those measurements we can do probably. Well, there are several ways to look for the quadruple fluctuations, and I think we have some very good results on that. So I'll try to do 15 minutes and 15 minutes. And I'll take any questions, and you can ask questions during the talk, please. So so this idea of this experiment goes way back. So those called Caroli-Desjardins states inside the vortex core. There is a confined normal state, and it was predicted that there are discrete states inside the vortex core. Those are chiral states. They have orbital momenta, and the energy, this gap energy, is roughly the square of the delta over EF, or h bar square over the effective mass and correlation lengths. So this gap gets larger when we are dealing with very, very short correlation length materials. And people try to measure it conventional superconductors, and because these states are essentially very close to zero, no optical methods were really leading to any results. But then in the era of high TC, Dennis Drew put a lot of effort in trying to measure this in YBCO, and the main idea there was that this becomes possible because the critical field is way up in scale, 100 Tesla. So the correlation length is very short, and therefore this gap becomes measurable in terahertz spectroscopy. So there were many attempts. So Dennis worked on that project for more than 10 years, published a series of papers. But the result, I would say, was still inconclusive. Well, I'm showing some of those results here. The model that he used is that there is a superconducting current, there is a vortex core state, this is a normal. So this is inside the vortex core, there is this resonance excitation, which is chiral, which you can probe with circularly polarized light. And for Hall type superconductors, the transition is going to be, the absorption is going to be in right polarized light. And if it's electron doped, it's going to be opposite. So you can determine that. And then there is an interaction. So this vortex is a pin. There is a question, there was a question, how can this be measured even on unpinned vortices if the translation invariance is present? So there is some controversial answers to that question. And then, so there is an interaction between the vortex core and the superfluid around that. And well, some quite complicated models were developed. So what we try to do is, unlike these iron telluride cellularide materials that we probably will hear later in the week, Hong is going to be here, right?
Actually, he got sick.
Ah, I see.
But
Okay.
this will be a student talking. Yeah.
All right. So somebody is going to talk about his results. So there are STM data on this Vortex core by Hanaguri group. We're trying also to see either directly zero bias anomaly or these Caroli-Dejean states. The results were quite messy in many cases because these materials are quite disordered. So the measurement here is done on MBE grown film, which is a significant improvement towards getting more homogeneous results. Right. Again, so motivation is that those are two. They are simultaneously electron and holes. So this is a composite system. So that around the gamma point we have the hole band. Well, actually more than one. Electron point we have. At M point we have electron bands. But the interesting thing here is that while gap is fairly large, the Fermi energy is small, and that gives us a measurable distance for that resonance, so it can be measured. Again, so I already mentioned the motivation. This is this data from Hong Ding's group, where they claim to see the zero bias anomaly, which they call Majorana bound states, and they see also the Caroli-Dejean excitations. They claim that, well, there is also interesting thing here in this approach is that if there is a indeed zero bias state, then the quantization of Caroli-Dejean state is different. So it's not minus half plus half, but it's minus 1, 0, 1, etc. So it's a different also. Okay, so this is the film that we have. It's about 40 nanometer of material, which is reasonably transparent for terahertz radiation. It's done on substrate. So the film comes from Rutgers, from Sean Och's group, who worked very hard to develop MBE-grown, very carefully designed materials where there is no strain to substrate, and etc., etc. So this is very complex work. And the measurement is performed in this case in the geometry where this is the sample, and we send linear depolarized light on the sample, and then behind the sample we have a second polarizer. We measure 45 or minus 45 degrees relative to incoming linear polarization, and from that one can calculate the Faraday rotation for the transmission. And from that we can look for the spectra, and the spectra should reflect give the information about the Caroli-Dejean state, and possibly even about the zero bias state if that such exists. All right, so this I should mention that these oscillations in data are due to Fabry-Perot reflection in the substrate. So one has to ignore those when looking on the data. But so we measured several samples, and this is the composition close to what that composition where Hong Ding claimed to see Majorana states. We do see definitely a rotation which is related to Caroli-Dejean state. We can see how this rotation, how this amplitude of this rotation depends on the applied field, basically the density of the vortices, how it depends on temperature. So it disappears at DC, and it's kind of increasing in the state. But then we developed another sample with a different composition, and interestingly, there is a change of sign in Faraday rotation here, and this is isovalent substitution. So what happens here, I believe, is that there's a way to play with the sizes of the electron and hole pockets, and by bringing in different energy scales and different gaps on different Fermi pockets. In one case, it was dominated by holes. Well, the previous was dominated by electrons. This one is dominated by holes. Again, there is a nice temperature dependence and field dependence of the state. So very quick conclusion is here. I'm trying to leave leave time for the second part, but I would take questions to this because the other part is very different. So if there's
There are questions.
if there are questions, yes.
Do you see
So
the...
did you see this minor state or not?
I can't say anything about that. Not at this point. Yes, I said it's yes.
Do you see this